Welcome to a new test and teardown video. This time it's another advanced instruments. An LF oscillator J2E. This one covers 15 Hz to 50 kHz in 3 ranges. It is sine wave only. I really expect this one to be nice and clean. But it's tube based. I think it's from the 60s. And I got this from the good old Peter. Thanks a lot. And he said it actually works. So I think we're just gonna plug it in and see if it's true. Ooh. It started with 44 watts and 30, 25, 20. Oh, look at that. Look. What I did, I am now in the 300 to 4000, and that is that scale here. And what I really tried was to reach exactly 1000. And I mean, this one is nearly 60 years old, right? And that is the frequency. 987. So that is quite close. And the sine wave is nice and fine. I don't have any little blip blops here at the starters, at the tops. And that is a classic transistor thing. And it looks really, really nice. I will definitely see how the output looks like. Here is the single-ended output. The SPL is actually pretty good. As you can see here, total harmonic distortion is 0.41%. So that's really not bad at all. But we do see 50 Hertz and 100 Hertz. And we also see how mains frequency is kind of modulated and mixed together with the 1 kilohertz. And obviously this is a tube amplified oscillator, and the whole oscillator is tube based. So surely we would expect to see some harmonics. A second harmonics will be higher than third harmonic, and that is exactly what we see. But we also see mains frequency again modulated together with the harmonics, and all this sums up to a 0.41. Maybe I can make this a little bit better by changing the capacitors or something like that in this unit, because if I can get ripple down, then it would obviously help a lot on that, right? So here's the single-ended output. But what we can do is we can go over to the completely floating differential output and see if that is better. Probably it's better isolated. Maybe it's isolated better from mains hum and so on. So now we'll try and have a little look on that output. Let's see if that is any better. So here's the differential output. What I did is I'm using it I'm not using the attenuator, but I'm dialing down the output for exactly the same reading, because this one delivers quite a lot more voltage. So when I have everything adjusted at the same level, as you can see here, the differential output is actually a little bit better. 0.31 total harmonic distortion. So that is expected to see that a little bit better. So now we'll try and open the unit, right, and have a little look. Inside the bottom of this unit, I just accidentally touched this, and look at that. Nasty. It's still really, really warm. Holy moly. Ow. We got some very warm components in here. It's full of dust as well, so I have to clean it up a little bit. I would expect this one to be the output transformer, right? But what I did find, let me show you the other side in a second. I bet this is the high voltage. See, we got some filter components right there, right? And that looks a lot like high voltage rectifier. And it's probably just running mains frequency on filaments. So that could also explain a little bit about all that ripple. Inside the top view, I cleaned a little bit of the dust away. We can see the 3 tubes. And as we see here, they're quite modern type. So this is not the original 1956 version. It has been upgraded a little bit over the years. What we see here is, of course, the mains transformer. I should definitely pull the plug before touching anything. So that one is, of course, the mains transformer, and we see the AC high voltage, a positive and a negative, plus minus 300 winding with a center tap, and we got 2 filaments, 6.3 volt each. And that is, of course, because we got an individual filament for the rectifier tube. That is an EC81, a double diode rectifier. And then we got the output pentode is an EL86. We got a tiny little triode down there. That is a 6C4. And that one is the oscillator dual triode, ECC88. I can also show you the schematic. I'm sorry it's not in the most super duper tip top quality, but you can see here I wrote down the original tubes. That will be the 1956 versions of the super big and really old tubes, obviously. And then they found a more modern replacement for all 4 of them. What we can see here is, of course, the mains transformer, the EC81 rectifier with its individual filament. And then we got, it's actually a little bit interesting with those capacitors. We got those 4, well, I will say 4, but I'm going to explain you in a second, okay? Because we got here on the schematic, it looks like 3 capacitors, but it is actually 4 individual capacitors. Here we got 2 in parallel, and this is a little bit funny. Maybe I should show you this in real life, how it's really done. So now we remember the schematic with the rectifier diode here, and then we got the 2 red wires. I think that will be from the transformer, and that will be the high voltage coming out of the cathode, that orange wire. So that one goes to the first capacitor, and we got 2 in 1 capacitor, and that's just super old style with more capacitors in one casing. So they are each 16 microfarads. So the first one, and then we got this 500 ohm resistor. That will be the R28. And then look at that. We are now using this 16 micro and that 16 micro as the next capacitor. And then we have here, that will be R21, and this is 2K2. And then you go to the last capacitor. of the 3 on the schematic. And here we got some wires using the different voltages, but that is what we got for the anode supply. I should probably just show you once again on the schematic for a super fast repeat. The first 16 are 28, 500 ohms, 2 in parallel, and the 2K2, and the last capacitor. So I think I will try and play a little bit with this system as well, because we got 4.5 volts of AC ripple here, we got 304 volts DC, and then got only 0.4 volts AC, right? So we still got a lot of ripple on this point. But it's actually quite interesting, this coupling here. They're using this point with ripple, with the feedback here, to try and remove that ripple actively. That's a little bit interesting. Instead of putting this low pass filter here to ground, they're using this signal here with ripple and injecting this and subtracting that from the signal. That is a little bit smart. So there's you will think that this is an amplifier, but this is really a feedback system to remove distortion in the output drive pentode. So that is also a very, very smart. And the oscillator, that will be the dual triode ECC88. And yeah, we got the 3 different frequency ranges here. Really, really high resistors here in the low frequency. And that is, of course, the way the amplifier works here. We also got feedback, by the way, again to try and remove distortion. But the real signal path is, of course, this way. And that will be the output attenuator, and this way you get the output. I removed the shield around the capacitors and the range resistors. Of course, they need a good solid shield around here, so you don't have a lot of direct coupling from the mains transformer into that system. So that is, of course, a big problem for this design. That is the distance. But what could they have done? That transformer could probably have been all the way up here, right? I mean, that could have been done. Yeah, that is probably, from here it looks like it's bad planning, to be honest. At least the rectifier tube is as far away as possible. Also, I must say, this transformer looks a little bit huge. This unit only uses 40 watts only. Well, that is how it is with four tubes like that. Half of it is probably in the rectifier and the output power pentode. Well, that is how it was in the oldie days, huh? I don't know, did I explain about the output transformers? Yeah, we got 2 of them. So the big one is for the low frequencies. And there's a tiny one at the bottom, and it changes over. When you change the frequency ranges, you go from the big one to the small one, because you can't really do a so wide frequency range with transformers. Certainly not easy and cheap. So it would have been cheaper just to make more ranges and 2 different transformers instead of one made of special stuff. And here is the tiny little output transformer for the highest frequency range. So of course you don't need a large transformer when the frequency is much higher. I tried to replace the capacitors instead of the original ones. See, we got 2 times 16. So here I got 33 So I'm kind of doubling up on everything here. So this should halve the ripple on the AC. That's quite simple, isn't it? So that is what we need to see if we have attenuated the 50 Hertz and 100 Hertz. This is, of course, not going to affect the higher frequency harmonics. There's another little problem. Look at that. One of the mounting brackets, or what will you call this, a little screw thingy here, is missing. So that means this shielding for the capacitors is not proper grounded. So that we cannot have. I'll see if I can fix this. I got a tiny little idea, because I cannot save brass pieces like this. This is about the same diameter, but of course I saved the brass nut for that. Maybe I could cut this and solder it like that. That could probably be possible, right? So this is one of the things I really love about having a Metcal. You can just solder onto anything. So I think they tinned, or they nickeled, or they somehow treated this piece of metal so you can actually solder it, and then they painted it and something like that. So yeah, that was easy. Now I think we can assemble all this again. So here is the spectrum of the generator with 4 new capacitors in the high voltage system, and they have, of course, double the capacity and also half the internal resistance. And as we see here, total harmonic distortion is not a lot lower. It's actually a tiny little bit worse. But what we see is all the lower frequency below 500 Hertz is actually much less. And we have less 100 Hertz and 50 Hertz, and all that is of course better. But what I think happens is that the better capacitors with lower internal resistance and all that actually allows the amplifiers to amplify a little bit more at the higher frequencies, at the higher harmonics, and that way the sum of everything is actually a tiny little bit worse when it comes to total harmonic distortion. But yeah, hum is less. That is just so unfair. All this work for nothing. I really can't let this go. The noise, the ripple, the total harmonic distortion. So look what I'm doing here. I've disconnected all the secondaries from the transformer. So this is my high voltage and this is my filament. So filament is now running off a DC power supply, and high voltage is running off a DC power supply. And I'm hereby verifying I got exactly the same anode supply on that capacitor with this. It's measuring down here, right? So my output is still connected to my PC and all that fancy smancy things. So look at the curve. This is mains transformer off. All right. As you see here, we do not have any visible 50 Hertz, 100 Hertz, and all the mixing into the wanted frequencies and all the intermodulations and all those kind of things. It's more or less gone. Of course, we got the harmonics, the second harmonic and all that stuff. Perfectly fine. All right. Now, let's try and turn on the mains transformer like that. And all we see here on the front is, of course, the red lamp. And we're using 2.8 watts on the mains transformer. That is just the idle power usage of that transformer. But now look at the spectrum. And now we see mains frequency and harmonics and all the nasty stuff is definitely back. So how is that possible? Is it magnetic? Is it acoustic? Or is it currents that flows in the transformer that is somehow connected to the chassis electrically, and that's why going through the chassis and stuff. So I got a few different ideas, and I'm going to hunt this down. So look what I've done here. Now the transformer is completely unscrewed and lifted off the chassis and put on some soft paper. And it is exactly the same. Of course, I removed all the wires just so you can see it is completely disconnected. And I still get this 50 hertz, 100 hertz, and all the harmonics and all this mixing and all that stuff. So this just proves it's now magnetic radiation from the transformer that is picked up by something in this area behind this or under there, or it just goes through metal all the way over here. Perhaps this is the output transformer. Yeah, that's just what it is. It's impossible to shield and fix, but it is of course also a lot of dB down, obviously way below specifications. It's just because I can see it. I wanted to try and see if I could fix it, and I wanted at least to try and see if I could understand the source and the coupling of that signal. But now I know for sure it's magnetic. So that is just what it is, and I can just document my finding, and I learned something today. That is what there is to say about that. So now this unit is back to normal. I learned a lot and I had a lot of fun. I hope you also had a little bit of fun. Thank you very much for watching. Bye bye.